Achieving net zero emissions by 2050 on a global scale requires not only reducing anthropogenic carbon emissions, but also removing the carbon that has accumulated in the atmosphere since the Industrial Revolution. In this episode, we provide an overview of several carbon dioxide removal or CDR technologies, how they work, their costs, and the associated challenges with deploying them at the scales we require. The first question is, how much carbon do we need to remove from the atmosphere to limit global warming to 1.5 degrees Celsius? Climate Now spoke with Dr. Roger Ains, who leads the Carbon Initiative at the Lawrence Livermore National Laboratory.
1.5 degrees C is dauntingly difficult to do. And in order to do so, we're going to have to remove a lot of the CO2 that we've already put there, make up for the fact that we were too slow. And the amounts are staggering. By the middle of the century, 2050, we'll have to remove 10 billion tons per year of CO2 from the atmosphere. What is 10 billion tons? We produce 5 billion tons of oil worldwide a year. So that means 10 billion tons means between now and 2050, we have to create this entirely new industry, whatever it is, to remove this, something that's twice the size of today's oil industry.
So, understanding the scale of the problem and why it's important, let's discuss some of the most commonly cited CDR options and their associated costs. We can separate CDR methods into two categories: natural carbon sinks that we want to enhance, such as forests, soil sequestration, and mineralization, and those that are more technologically intensive, such as direct air capture, bioenergy and carbon capture and storage, otherwise known as BECCS, and underground geological storage of CO2. Each of these methods comes in multiple varieties, and much of the work on them is still in the experimental or very early commercial phases. So the numbers that we have in terms of amounts of CO2 sequestered and costs are yet to be proven on a commercial scale. We include all of our sources at the end of our videos and in the transcripts on climatenow.com, so you can always go deeper if you wish. Before continuing, it's important to note that oceans also play a huge role in absorbing carbon from the atmosphere. Naturally, the oceans take in an average of 25% of what is released annually into the atmosphere. The way the oceans and the atmosphere interact is very complex, but what is certain is that we do not want to increase the amount of carbon stored in the oceans, as this is contributing to ocean acidification and the extinction of species. Now, let's break down our main CDR methods. Forestation refers to the planting of trees on lands that are degraded or reconverting land that was once forested but is now used for commercial purposes. In the United States, there are an estimated 133 million acres available for reforestation, which means roughly 333 million additional tons of CO2 could be sequestered annually. Globally, there are 1.67 billion acres of land available for forest restoration. If these global forestation efforts were to succeed, studies suggest that by 2050, these forests will have a net potential to store between 0.5 and 3.6 billion tons of CO2 annually. Compared to the need to remove 10 billion tons annually, this represents, in the very best case, about a third of what we need to be storing. In terms of cost, this is one of the most affordable methods of CDR at $5 to $50 a ton of CO2 sequestered. A 2018 paper in Environmental Letters Research specifies that differences in cost effectiveness could be due to multiple factors, such as yield rates, land prices, transaction costs, and reporting differences. That said, there are several challenges with forestation, one of which is carbon accounting. Methodologies to accurately measure the CO2 sequestered by forestation efforts are not standardized, and determining the duration for which trees are able to grow and continue to absorb CO2 and store that CO2, otherwise known as permanence of sequestration, is challenging. Moving on to more technologically intensive solutions for CDR, one of the most widely discussed is direct air capture, or direct air capture with storage. A wide range of technologies are currently being developed to directly capture CO2 from the ambient air, and their capabilities have the potential to remove between 0.5 and 5 billion tons of CO2 annually. In the best case scenario, we're looking at another strategy that can handle about half of our global sequestration needs. However, capturing the CO2 using this type of technology is very expensive. Dr. Howard Herzog, a senior engineer at the MIT Energy Initiative and one of the pioneers of carbon capture and sequestration, has this to say about it.
So carbon engineering think it can do it for between $100 and $300 a ton of CO2. I've done a lot of analysis. don't think those numbers are credible, at least not any in the near future. People ask me what the range will be in 2030. I give them a range of $600 to $1,000 a ton of CO2. Even at $600 to $1,000 a ton of CO2, it still may be cheaper than getting the jet fuel off the airplane.
Defenders of direct air capture emphasize that this is just the starter cost. As technologies improve and scale up, they say they have the potential to go down to $100 to $300 per ton. Many experts agree that this CDR method isn't the most cost-effective, but major oil companies like Chevron, Shell, and Total have been willing to invest, given the increasing global pressure to be part of the solution. Another CDR method is BECCS, Bioenergy with Carbon Capture and Storage. Bioenergy is derived from biomass that is converted into electricity or a liquid fuel. CO2 released in this process is then captured and stored underground. Natural resource economist Dr. Matthew Langholtz at the Oak Ridge National Laboratory puts into perspective how much carbon can be stored using BECCS in the United States.
There's been previous work estimating about up to about 700 million tons potentially of CO2 sequestered annually. Basically, in the near term, using the near-term resources, you could sequester about 200 million tons per year. If you had energy crops, you could sequester up to 700 million tons per year. Another way to put it in context is the IPCC Pathway 2 says the world might need 1 billion tons of CO2 sequestered per year to achieve carbon neutral in one of their scenarios. Here you could do most of that from the US alone. So it's not everything. It's not enough for the solution, but it could be a key part of the overall decarbonization solution.
To put that into context, 700 million tons per year is 13% of the United States' total CO2 emissions in 2019. Globally, BECCS can store an estimated 0.5 to 5 billion tons CO2 annually. So not only does BECCS have the potential to remove half of our target 10 billion tons CO2 annually, but current cost estimates for this technology put it as low as $15 per ton CO2, according to the Global CCS Institute. This low cost assumes that the resulting biofuel is used in the most suitable power plants and that there is easy access to abundant biomass in underground storage sites. It also assumes biomass fuel costs that are lower than the price of coal. On the other hand, the cost of BECCS can go up to $400 per ton CO2, depending on the biofuel production method. It is also important to note that since biomass is largely sourced from special forestry byproducts or crops grown specifically for this purpose, there is little to no risk that biofuel production will compete with land use or forestation efforts. Next, we have soil carbon sequestration. Rich and untilled soil is a highly dense and natural carbon sink. Studies estimate that at a depth of just 2 meters, the Earth's soils currently hold 2,600 billion tons of CO2. How is this possible? Well, soil organic matter traps carbon via several ecosystem processes, such as photosynthesis, respiration of microbes and fungi, as well as decomposition of organic material. However, rates of soil carbon uptake change with climate and human activity. The equivalent of 175 to 350 billion tons of carbon dioxide have been released through the conversion of natural to agricultural ecosystems. Total losses of soil organic carbon as a result of land use changes account for 1/3 of anthropogenic CO2 in the atmosphere. While these losses are significant, studies estimate that by 2050, up to 5 billion tons of CO2 could be sequestered in soils annually. That's already half of our 2050 global CO2 sequestration needs. Though it's important to note that soil carbon uptake declines after 20 to 40 years as soils build up to their maximum potential. To maximize soil carbon sequestration, a variety of practices need to be implemented, including low-till or no-till crop management, improved planting schedules, and management of grazing livestock. Estimated costs of making these changes are between $0 to $100 per ton CO2. Another long-term and natural solution to CDR is a method known as mineralization. Here, CO2 reacts with compounds like magnesium oxide and calcium oxide found in minerals like olivine, serpentine, and limestone to trap CO2 into a solid state. The end products of these reactions are environmentally safe and do not require post-storage monitoring. Today, there are several companies trying to use this method to monetize products made from the resulting compounds. As you can see in this diagram, by using CO2 as a feedstock to create a product that is 2/3 magnesite and 1/3 amorphous silica, this process can be used to manufacture concrete, paper, and polymers. The problem is that it's very difficult to penetrate these industries from both a cost and supply chain perspective. We cover these issues in a podcast with the founder of one company involved in these efforts, Green Minerals. It is estimated that the cumulative annual production rates of industrial waste materials have a total CO2 uptake capacity of 0.5 to 1 billion tons per year, at a cost as low as $48 per ton CO2. But a potentially unlimited amount of CO2 could be stored per year via mineralization in natural basalt formations, limited only by our ability to get the CO2 to these formations. The cost of this type of mineralization ranges from $7 to $30 per ton. The last component of the current CDR portfolio involves the geological storage of carbon. The storage technology is integral to both BECCS and direct air capture strategies, as it provides a means to store large amounts of pure CO2. By looking at this diagram, we can see that this is done by taking CO2 captured at power plants, turning it into supercritical CO2, transporting it either to onshore or offshore storage sites, and injecting it into the ground or deep water. In this image, we see that there are 4 available methods to store this CO2. The methods are injection into deep salt formations or into unminable coal beds for enhanced methane recovery. CO2 can also be used to enhance current oil and gas recovery, or can be injected back into depleted oil and gas reservoirs to restore pressure levels. These geological formations are located all around the planet and have the capacity to store a total of 25,000 billion tons of CO2. The challenge here, however, is strategically choosing storage sites and determining the rate at which CO2 can be sequestered. Sequestering carbon in deep sedimentary basins comes at an estimated cost of $7 to $13 per ton CO2. The price tag includes the cost of well drilling, injection, monitoring, maintenance, and other incidental costs. However, it does not include any remediation costs, should any well leakage or groundwater contamination occur. Geological storage of CO2 also comes with the risk of inducing seismic activity, which means the pressure within these wells would need to be monitored closely. However, the technology and methods are well understood. The oil industry has been sequestering carbon dioxide underground since the 70s as a technique to enhance oil recovery. These 6 CDR strategies, forestation, soil carbon sequestration, mineralization, direct air capture, bioenergy with carbon capture and storage, and geological storage, only skim the surface of what's currently out there. Their associated prices and sequestration potential are also likely to become more certain as technologies evolve and policies are introduced to support their development. What cannot be stressed enough is that at the end of the day, the only way we'll reach net zero globally by 2050 will be by investing in all of these CDR technologies. While we focused on the best case scenarios in this video, which would allow us to store close to 21 billion tons of CO2 annually, worst case scenario estimates wouldn't get us even to half of our global sequestration needs. For a deeper dive into this topic, check out our full-length podcast episodes with experts Howard Herzog, Roger Ains, and Matthew Langholtz, where we dig deeper into the evolution and the current state of CDR technologies. To find out more about each CDR strategy mentioned in this video, check out our technology video series that will delve deeper into each one. To sign up for our new releases and more, visit climatenow.com. Thanks, and see you next time.